Thank you all for coming to my thesis defense. Today I'll present my thesis defense, which is three problems in unconventional coordinate system, and they are conduction in a spheroid and conduction from a torus, and flow in a semi-elliptic tube. This presentation will be divided into 4 parts. In the first part, we will generalize the idea of the curl and divergence for any coordinate system, and in the remaining 3 parts, we will discuss our 3 problems. Now, in the first part, we will find a generalization for the curl and divergence operators for any coordinate system, whether it is orthogonal or non-orthogonal. Now, it's needless to say that the coordinate system, it is needless to say that the physics must be independent of the coordinate system. That means the temperature is a temperature whether you are dealing with a Cartesian coordinate system or any other coordinate system. However, the Cartesian coordinate system has the advantage that the unit vectors I, j, and k are constant, and its scale factors are unity. On the other hand, using other coordinate systems may help in solving some particular problems. To choose the appropriate coordinate system, one should look at the boundary of the problem and the separability of variables in that coordinate. Now, let us look at these 2 typical examples. The first one governs the flow in a medium, and the second one is the heat equation. And we can see that these equations contains the curl and divergence and the Laplacian operators. Now we need to express these operators in the coordinate system that we have chosen. Now these operators are well known for orthogonal coordinate system, where the coordinate surfaces meet at right angles. These are some examples for orthogonal coordinate system, and these are the expressions for these operators. These expressions are given in terms of the scale factor, which is the square root of the metric coefficient. Now let us look at this particular example. Assume we have 2 parallel infinite cylinders, and we have a flow parallel to the cross section of these cylinders. Now, pi-polar coordinate system could be the most appropriate coordinate that can host this problem, and we can apply the previous operators used in this coordinate. Now, assume if we have an oblique flow. Now, to avoid dealing with a 3-dimensional problem, one should consider the cross-section parallel to the flow, which is now an ellipse. Now, this pi-polar coordinate system is not the most appropriate coordinate system, and we need to have another coordinate system, which is most probably the pi-polar elliptic coordinate system. Now, this coordinate system is not orthogonal, and now we cannot apply these operators or these expressions, and we need to define another expression for this non-orthogonal coordinate system. Now, assume we have a general coordinate system u1, u2, u3, not necessarily orthogonal, and r is the position vector. Then we define the tangent unit vector in the direction of ui by taking the rate of change of the position vector in the direction of ui divided by its magnitude, and this magnitude is known as the scale factor, which is the square root of the metric coefficient. Now, a divergence theorem may help us to find a generalization for a divergence for any coordinate system. Divergence theorem relates the net flux through a surface to the volume integral of the divergence. Now, we can define the normal vector. Consider this bottom surface here. We can define the normal unit vector n and the elemental surface area ds, where W is our vector field composed from 3 components. Now, again, on the bottom surface here, we can evaluate the left-hand side of the divergence theorem to be this expression, and we can use Taylor series expansion of first order to find this value on the upper surface. Now, the net flux through the upper and lower surface will be just the summation of these 2 quantities. Now, doing the same thing with the other 2 pairs of surfaces, we can find the left-hand side of the divergence theorem as this, and as the summation of these 3 expressions. Now, observe that this trouble, that scalar dot product, appears 3 times, appears in each expression of these. We give it a name as orthogonality indicator. Now, back to our divergence theorem again. We need to evaluate the right-hand side of the divergence theorem. We can do so once we have the elemental volume dV, and this is the expression. Now, equating both sides, we can get the generalization the divergence for any coordinate system, not necessarily orthogonal, and the only difference between the generalization and the orthogonal expression is depend on this orthogonality indicator. Now, on the other hand, Stokes theorem, we can use Stokes theorem to generalize the idea of the curve for any coordinate system. Stokes theorem relates the surface integral of the curve to the line integral on the boundary of the surface. Now, we can consider again this bottom surface. We can equate the left-hand side of the Stokes theorem as this expression. Note that the only component which survived was the third component of the divergence. Now, we need to evaluate the line integral on the bottom surface again, which is composed of these four line segments. We can, for example, along C1, this is the expression, and along C3 here, we can use Taylor series expansion of first order to find the value of the along this line. Now, doing the same thing along C4 and C2, we can have the line integral through the boundary of the surface. Now, by equating both sides, we can have an expression for the third component. Remember, the only component which survived with us is the third one. Now we can use the other two surfaces to find the general expression for the first and second component, and we can put everything here together in indeterminate form, in this indeterminate form, and again, the only difference is based on this orthogonality factor E. To summarize, the only difference between this generalized expression and the orthogonal expression is based on this orthogonality factor, orthogonality indicator E, which ranges from 0 when the coordinate system is 2-dimensional up to 1 when the coordinate system is orthogonal. Now, this is our first problem, heat conduction in a spheroid. In this problem, we will, these are the two types of the spheroid. This is prolate and oblate. We will heat our spheroid to a constant temperature T0, and then we will leave it to be cooled in an infinite medium of constant temperature T infinity. Now, why we are studying this problem? It is, in fact, a spheroid is a more general geometry from a sphere, and it is related to many applications in the industry. For example, the pack pits and drying process. Now, these are the two types of our spheroids, prolate or oblate. We can get a prolate by revolving an ellipse about its major axis, and we can get an oblate by revolving an ellipse about its minor axis. In both cases, the semi-major axis equals to A, and the semi-minor axis equals to B, where C is the focal distance, and xi naught defines the surface of the spheroid. Right. This is our model. It's just the heat equation, and these are where T capital here is the temperature, T small is the time, and alpha is the thermal diffusivity, and it is related to the thermal conductivity and the density and the specific heat of the material. Now, these are the boundary conditions that we, the temperature on the surface of the spheroid is always kept at constant temperature T infinity of the medium, the temperature of the medium, and we heat our spheroid initially to a constant temperature T naught, and again, the solution here inside, the temperature inside is always finite. Now, we will use the appropriate coordinate system that can coincide with the boundary of this problem is the spheroidal coordinates, which can be prolate or oblate. The prolate spheroidal coordinate system is related to the Cartesian coordinate by these relations, and we can easily calculate the scale factors as this. Note that the variable xi ranges from 0 up to infinity, and the variable eta from 0 up to pi, and the variable theta from 0 up to 2. This coordinate system consists of these coordinate surfaces, prolate spheroid, when xi is constant. It ranges from a very thin needle here, when xi is equals to 0, up to the limiting case of a sphere when xi approaches to infinity, or the axis ratio equals to 1. The second coordinate surface is the hyperboloid of two sheets when eta is constant, a branch of hyperboloid of two sheets, either the upper one or the lower one. And the third coordinate surface is half plane through the z-axis. These are cross-section. Here eta is 0, eta pi over 2, eta equals to 2 pi, and here xi goes from a thin needle when xi equals to 0 up to a limiting case of a sphere. Okay. Now, On the other hand, the plate spheroidal coordinate system is related to the Cartesian coordinate system by these relations, and we can again easily compute the scale factors here. Now it contains three coordinate surface of plate spheroid when xi is constant. Now it goes from a circular disk when xi equals to 0 up to a limit in case of a sphere when xi approaches to infinity, or the axis ratio equals to 1. The second coordinate surface is the hyperboloids of one sheet, half hyperboloid of one sheet when it is constant, and half planes through the z-axis, and these are three-dimensional graphs from this xi from 0 up to limit in case of a sphere, and here eta is changing from 0 up to y over 2 up to eta equals 2. Now, again, these are our two spheroids. A and B are given by these expressions. Now we can calculate the focal distance c, and we can relate xi naught, which defines our surface. Xi naught defines our surface of the spheroid. It is related to the axis ratio b over a. Now, it is a tradition in fluid dynamics and thermal sciences to work with non-dimensional variables. This is because we need to get rid from using some particular units of measurements. Now we will define our dimensionless temperature U by relating the temperature to the medium temperature T infinity and the initial temperature T naught, and we will define our dimensionless time by scaling the time using the thermal diffusivity and the semi-major axis A. Now these are the energy equation in prolate spheroidal coordinates, and the second one is the thermal equation in pro-plate spheroidal coordinate system. Now again, we can write our boundary condition and initial condition in terms of dimensionless value. We will solve only the first heat equation, which is in prolate spheroidal coordinates, keeping in mind that the second one can be done using the same approach. Now, the first solution, we will separate our dimensionless temperature U as a function of xi and eta, as a function f of xi and eta, and the function gamma of time. Now, doing the separation of variable, and we will get this separation constant. Now we can write our solution as the function f and an exponential decay in time over all values of these eigenvalues. Now assume further that f can be separated using a function zeta of xi and the function phi of eta. We can now do separation again, and we will get this separation constant, another separation constant, beta. Now, using these two transformations and rearranging this differential equation, we can get these two identical equations except for the ranges of the value. We will get two identical differential equations except for the ranges of the value. Note that the second separation constant beta is the same in both cases, and it depends on the first separation constant. Again, just a note, if lambda here equals to 0, then this expression here will be just the famous Legendre function. Fine. Now, look at this first differential equation here in phi. The eigenfunction of this differential equation is the angular wave function of first and second kind, and there are special cases from the general angular wave function of first and second kind. In our case, m is equals to 0 because of the rotational symmetry. That means the azimuthal wave number is equals to 0. Now these are typical graphs of the angular wave function of first and second kind. We can see that the angular wave function of the second kind is unbounded on the considered domain, and our solution phi must be only related to the angular wave function of first kind. This is not surprising because the angular wave function of the second kind is related to the associated Legendre function of the second kind, which is not bounded on the considered domain. Now consider the second equation with this domain. Now the eigenfunctions are the radial wave function of the first and second kind. Again, there are special cases of the general radial wave function of first and second kind. This general radial wave function of first and second kind is related to the spherical Bessel function of order n. Again, in our case, m is equals to 0 because of the rotational symmetry. Now these are typical graphs of the radial wave function of first and second kind, and again the second kind is unbounded on the considered domain, and our solution Z must be only a function of the radial wave function of the first kind. Now this is our solution again. It is related to the angular wave function of first kind, radial wave function of the first kind, and an exponential decay in time. Now what is remaining is to determine these eigenvalues, lambda in k, and this coefficient of the solution. Now, to determine these eigenvalues, we will use the boundary condition on the surface, and then we will find that these eigenvalues will satisfy this relation. Now, after that, these are typical values for the eigenvalues lambda in k for different n and k and different axis ratio. We generate these tables using Mathematica. Really, it has taken a long time to generate each table of these. About 7 days to generate each table from these tables. Now what is remaining is to determine the coefficient of the solution. To do so, we need to define or to find an orthogonality relation. Now this is our energy equation in Prolet's coordinate again. We separate the variable using f and gamma. Now we can find using by substituting this in the differential equation, we can find that the function f satisfies this differential equation. The function f satisfies this differential equation. Now assume that fn and fm are two eigenfunctions corresponding to two distinct eigenvalues, lambda and lambda k. Using simple vector analysis, we can find that fn and fm are orthogonal with respect to the scale factors h eta, h xi, h n. After we have found the orthogonality, now we can calculate the whole coefficient of our solution, and now the solution is complete. Now we use Mathematica with this spheroidal wave functions, and Mathematica has a serious problem with this function because of some programmable deficiency. So we decided to use another technique to verify our solution, or to compare our solution with it, and we decided to use finite difference method. This is again our partial differential equation, our energy equation in Prolet's coordinates. Using these two simple transformations, we will get this partial differential equation. Now we will express our solution in terms of the Legendre function, and the coefficient of the solution will be a function of the two remaining variables. Now, using this proposed solution with the orthogonality of the Legendre function, we can get an infinite number of partial differential equations now in the modes of the series, in the modes of the solution. What we will do, we will consider, or we will solve this infinite number of differential equation using finite number of n, say from n is equals to 0 up to n maximum. We will use finite difference method. This method is a standard method in the literature. In this method, we will approximate the derivatives using Taylor series expansion, whether it can be forward difference or central difference or backward difference. Now, using the finite difference in this infinite partial differential equation, we will get this finite difference relation. Now, notice that we evaluate the space derivatives using the new time step. That means we are using a fully implicit finite difference, which is known to be stable. What we will do, we initialize the values of fn from n is equals to 0 up to n max for the interior points, and then we will calculate the new values of fn using the most recently available information, and then we will repeat this until we get the desired accuracy. Then we will increment the time and do this procedure again. Now, these are our results. This figure shows the isotherms inside the prolate of axis ratio equals to 1/2. Isotherms mean the temperature distribution inside the spheroid. And we can see that we have here a high gradient here, and it's subside with time. This high gradient disappears as the time progresses. Now, these are the isotherms for plate spheroids snapshot at the time equals to 0.1 for different axis ratio. Now we define what we call local Nusselt number. This local Nusselt number simply measures how much energy comes out from the surface of the sphere, and it is related to the gradient of the temperature normal to the surface. Gradient of the temperature normal to the surface. Also, we can define what we call average Nusselt number by averaging the Nusselt number all over the surface. By the way, average non-dimensional temperature, U bar, can be defined by averaging the temperature inside the sphere, averaging the temperature over the volume, and this measures how much energy is remaining inside the spheroid by the time if the time is progress. Now we will validate our result by comparing it with a limiting case of a sphere. A limiting case of a sphere, that means the two axis ratio are equals. This is again the energy equation now in spherical coordinate system, and these are the boundary and initial conditions. Again, define the dimensionless variable. Doing a simple procedure, we will get the solution here, and we can define the average non-dimensional temperature, the Nusselt number, average Nusselt number. Notice that the Nusselt number and average Nusselt number are identically equal, and they are related to Jacobian elliptic theta function. They are equal because of the symmetry in the spherical case. Right. Now these are local Nusselt number at t is equals to 0.1 for different axis ratio. This is a comparison between our two solutions, and we can see that we have a perfect comparison. This is a comparison between our two solutions with the limiting case of a sphere. Now these are local Nusselt number for the case b over a equals 1 over 2 for prolate and oblate. Notice that we have maximum rate of heat transfer rate at eta equals to pi over 2, because it is the flat part in the prolate, where in the oblate we have the flat part here at eta equals to 0, eta equals to pi, and this is correct because we have maximum rate heat transfer rate at eta is equals to 0 and eta is equals to pi. This is average Nusselt number comparing our two results with the limiting case of a sphere, and again we have a perfect comparison here. Again, this is the average non-dimensional temperature for a sphere, two types of spheroid having the same volume, prolate and oblate having the same volume. We can see that the oblate has loses energy much faster than the prolate. This is because if they have the same volume, in the oblate case we have a much higher surface area, as you can see. Now, this is our second problem: flow in semi-elliptic channels. These microchannels are known to have high surface area per volume ratio, high heat transfer coefficient, and low thermal resistance, and it is related to many applications in the industry. Just inject print heads, infrared detectors, diode laser, nature gas chromatography, and heat exchanger for cooling computer chips. Now, usually in the industry, they want to implement or they want to produce a semicircular channels. But for some industry defects, the resulting channels could be approximated using semi-elliptic tube or semi-elliptic cross section. Right. Now this is our channel. Now the channel is infinite, but this is a segment from our channel, and this is the cross section. Our model here is simply the Poisson equation, where W is the velocity, P is the pressure, and Z is the direction of the velocity, and mu is the viscosity. This part here is the driving force. Fine. Now we will use elliptic cylindrical coordinate because it is the most appropriate coordinate that will coincide with the boundary of the problem. It is related to the Cartesian coordinate system by these relations, and again we can easily calculate the scale factor HXI, HETA, HC. Now it is not a cylindrical coordinate system, it is an ellipse. The cross section is an ellipse, not a circle. Now these are the surface, the coordinate surface. Elliptic channels when xi is constant, it goes from a plate to its limiting case of a circle cylinder when xi approaches to infinity, and hyperbolic cylinders and planes parallel to the xy plane. Now here xi is constant and eta is changing. What we will do now, we will limit our domain to be a semi-elliptic, because the whole domain is an ellipse. We need a semi-elliptic as our channel. Now we will limit the domain from eta equals to 0 up to eta equals to 1, and this is our semi-elliptic channel. Right. Now, again, we can find that these are the semi-major axis and semi-minor axis, and we can calculate the focal distance C and x sin naught, which defines the surface of the channel by relating it to the axis ratio B over A. Now, again, we define the dimensionless variables. This is the dimensionless velocity is related to the velocity by scaling it using the semi-major axis and the viscosity and the gradient of the pressure. Now, this is the Poisson equation. This is Poisson equation written in elliptic cylindrical coordinate system, and these are our boundary conditions. These boundary conditions are known to be the no-slip condition. Right. Now, because this partial differential equation is non-homogeneous, so one can find that the particular solution is equals to this expression here, and you see which is the complementary solution that will be it is a solution for the homogeneous version of this partial differential equation, and you see again will satisfy these conditions. Now, doing the separation of variables, we can find that the eigenfunction are the sine function and hyperbolic sine function. Now, what is remaining is to find what is the coefficient of the series. We will use the boundary condition on the surface again, and using the orthogonality of trigonometric functions, we can find these coefficients, and this is the final solution. Right. Now, this figure shows the velocity distribution for the case of axis ratio 1/2, and we can find the maximum velocity at the position where the rate of change of the velocity with respect to xi at this axis of symmetry equals to 0. Right. Now, we can define average dimensionless velocity by averaging the velocity over the area of the cross section of the channel, and we will get this summation. This expression contains this summation. Now, these two figures shows the maximum velocity for different axis ratio and the average velocity for different axis ratio. Again, we can observe that as we expected, that the maximum will be for the case when B over A equals to 1, or a semicircular cross section. Now, defining dimensionless shear stress, simply shear stress measures the frictions on the wall of the channel. We can define it by to the gradient of the velocity in the direction of ui. Now, again, this is the dimensionless shear stress. We can find the expressions for the shear stress along the 4 segments of the channel. This is first segment, second segment, third segment, and the fourth segment. Now, this figure shows the shear stress along the surface of the channel, and again, the maximum friction appears here in the symmetry of the channel. Right. To validate our solution, we compare our exact solution to 2 approximate solutions. The first one was Mortensen claims that the relation between the compactness and the correction number is close to linear, what he called a close to linear relation. Now, in our case, the compactness is equals to the perimeter square over the area, and the correction factor is equals to the area of the cross section over the semi-major axis square all over the average velocity. And again, it is perfectly agreed that we have a close to linear relation. The second approximation was Bahrami. This is an approximate calculation for Bahrami. This is the friction number and Reynolds number based on the square root of the cross-sectional area, and IB is the bipolar inertia, bipolar moment of inertia. Again, this line is our exact solution by finding this friction number and the Reynolds number, and these circles are Bahrami's approximation. And again, we have a perfect agreement. Now, this is our last problem in this presentation. We will make it quite brief. It is just an exercise in dealing with an unconventional coordinate system. In this problem, we will heat our torus to a constant temperature, and then we will see how this torus affect the medium. The ultimate objective of this problem is to find how the time affect the temperature inside the sphere. That means we need, if we have a hot spheroid, we need to cool it down before we package it. Now this is one application of this problem. This is our spheroid. This is a cross section of our torus. This is a cross section of the torus, where r small is the radius of the cross section, and r capital, our 2r capital, is the distance between the two centers. Now this is simply the Laplace equation, which is the steady state version of the energy equation. Our boundary condition is that the surface of the torus is always kept at the temperature inside the torus, and the problem has a bounded solution, where T here is the temperature, of course. Now we will use a toroidal coordinate system. It is related to the Cartesian coordinate by this relation, and again we can define the scale factors as given here. Now it contains from these three coordinate surfaces spherical balls when eta is constant. These are balls, not spheres, balls. And from toroids when xi is constant, and half planes through the z-axis when phi is constant. These are our surfaces. These are some balls going from eta here, eta equals to 0, up to eta equals here to pi, up to eta equals to pi over 2. And here eta is constant and xi is changing, going from xi equals to 0 up to xi infinity. Here xi is going to infinity. Now these are the balls, and here xi is changing. Fine. Now again we calculate the focal distance c, and we relate xi naught, which defines our surface of the torus, to the radial ratio r capital over r small. Fine. Now again we define dimensionless temperature by relates the temperature to the temperature of the medium and the temperature of the torus. Again, this is the Laplace equation, or the steady state energy equation in toroidal coordinate system, and these are the boundary conditions. Now this energy equation is not straightforward separable in toroidal coordinate. It is known to be r separable. R separable means we need an extra factor to separate the variables. This is the extra factor. Now this is our solution with this extra factor. We can do the separation, and we can find that the eigenfunction is the cosine function and the toroidal function of the first kind. Now we can find the coefficient of the solution by using the boundary condition on the surface. These are the coefficient, and then this is the full solution. Now this is dimensionless temperature distribution for the case of the radius of the cross section equals to 1, and for different distance of the centers. By this we have complete our final part of the presentation. These are publications from this work. The first one is in the Journal of Fluids of Engineering. The second one in International Journal of Material Mechanics and Manufacturing, which is just published in this month. And the third one is under review in the Journal of Heat Transfer, and we are now preparing the fourth one. I would just want to thank the chairman of my committee, Dr. Rajal Assar, and Dr. Al-Jubaili, and the other committee member, Dr. Osama and Dr. Salim, and Dr. Tahir Mustafa, and also my lovely family who came from Jeddah, and my brothers from this university. And again, thanks, a big thanks for all of you for coming. And if you have any question, you are more than welcome.